We're starting our Exam 1 review with a question on finding the domain of a function. Function f of x is a quotient, and we know that the denominator cannot be equal to 0. And also it contains a square root, and we know that whatever is inside the square root must be greater than or equal to 0, okay, in order for it to be a real number. So this function both has a denominator and has a square root. So we have to make sure that what's underneath the denominator is not only greater than or equal to 0, but it actually has to be greater than 0 because that square root's in the denominator. All right, so we just write down 3 minus x must be greater than 0. Again, the strictly greater than is because it's in the denominator. And just solve this. So minus x is greater than minus 3, and divide by minus 1. And remember that when we divide both sides by a negative, the direction changes. Okay, so what do we have here? We have x less than 3. And that's our domain. Okay, let's look at number 2. Here we have a piecewise defined function, and in this example we're just practicing finding values of the function. Alright, so starting with f of minus 2, well, minus 2 fits into the x minus 3 category. Minus 2 is less than 3, so we use the top expression, 2x plus 5, to get the value of f of minus 2. So let's write that down. F of minus 2 is equal to, using the top expression, substitute in. So we have minus 4 plus 5, which is 1. And now we want to find f of 10. 10 fits into the second category. 10 is greater than or equal to 3, so use the second expression and substitute in 10. And we have 72. And finally, f of 3. Well, here, because of the double line here, x greater than or equal to 3, 3 fits into the second category as well, so use 7x plus 2 to find the value. Substitute in 3. And we have 23. In number 3, we want to find the limit if it exists. This is a piecewise defined function, and it's equal to 2x plus 5 to the left of 1 and x plus 6 to the right of 1, so it splits at 1. And we want to take the limit as x goes to 1. So our limit is going to involve both these expressions. So we're going to take the limit on the left and the limit on the right. If they're equal, then the limit exists. If not, the limit does not exist. So let's do that. The limit as x goes to 1 from the left, the little minus is from the left, well, we would use the top expression. We can just substitute in 1. And we have 7. Okay, now let's do the limit as x goes to 1. From the right, x greater than or equal to 1, use the bottom expression. Just substitute in. And then we just say that these are equal. This is a shorthand way of doing it. These are equal. Therefore, the limit as x goes to 1 of f of x is equal to 1. Okay, so the limit does exist, and it's equal to 1. Sorry, let me just correct myself. The limit as x goes to 1 of f of x is equal to 7. Here on the right and the left, the limit is 7, so the limit is 7. Okay. Okay, now we're taking the limit as x goes to 2 for this piecewise defined function. But notice that this piecewise defined function is different from the previous one. This function is equal to 3x plus 5 to the right of 2 and to the left of 2. And it's equal to 7 at x equal 2. So in other words, this function doesn't really split at x equal 2. It doesn't, we don't use two different expressions, to the right of 2 and to the left of 2. We use the same 3x plus 5, both to the right and to the left. So the limit as x goes to 2 here is going to be this expression with 2 substituted in. So that limit will exist. All right, to the right and the left, okay, there are two ways of looking at this. To the right and the left, we're using 3x plus 5. So we'll just substitute in 2 in both cases and get 6 plus 5, which is 11. But we're going to do this using the fact that, or using a theorem or a rule that we have that states that if f of x is equal to a polynomial, 3x plus 5, everywhere except for a finite number of values, then the limit is just going to be what we get when we substitute in our value into the polynomial. We'll just substitute 2 into the polynomial. All right, so that's how we're going to do this. So we're going to say, I'll just write down, since f of x is equal to a polynomial everywhere except a finite number of values. This is our rule. The limit as x goes to c of f of x is equal to p of c. In other words, substitute into the polynomial. So in our case, the limit as x goes to 2 of f of x is equal to p of 2. Just substitute into 3x plus 5. Okay, here's another piecewise defined function defined differently to the left of 3 and to the right of 3. We're taking the limit as x goes to 2. Here we have the limit on the left. Use the top line, substitute in 3, 6 plus 1. And use the bottom line for the limit on the right. Just substitute in. And we observe that these are not equal. Therefore, limit as x goes to 3 of f of x does not exist. In number 6, we're going to rewrite this expression as a piecewise defined function by removing the absolute values. So if x is greater than 3, notice this time I'm putting the greater first and I'll put the less than second. If x is greater than 3, then x minus 3 is positive, so those absolute values aren't doing anything, so we could just remove them. The expression is the same as x minus 3 over x minus 3, which is equal to 1. And if x is less than 3, then this expression is negative. So in order to make it positive, having the same effect as these absolute values have, we can just stick a little negative sign in front. Again, x minus 3 is negative, so minus x minus 3 would be positive. So what we're left with is minus x minus 3 over x minus 3, and that's equal to minus 1. So here we have a function that's equal to 1 to the right of 3, minus 1 to the left of 3. And notice that x equal 3 is not in the domain because that makes the denominator 0. So the limit as x goes to 3 from the right is 1. The limit as x goes to 3 from the left is minus 1. The two are not equal. Let me just write that out. The limit as x goes to 3 from the right is 1. And the limit as x goes to 3 from the left is minus 1. And these two are not equal. Therefore, the limit as x goes to 3 of x minus 3 absolute value over x minus 3 does not exist. In number 7, we're taking the limit as x goes to 8 of this quotient. Now notice that we can't substitute in x equal 8 right away because that would make the numerator and the denominator 0. All right, let me just, actually this is kind of superfluous over here. Let's cross this out. Okay, I just noticed that. So we have to do some manipulating and hopefully cancel out the x minus 8 from numerator and denominator. At this point, we don't have an x minus 8 in the numerator, so a standard trick, we've seen this in class, when we have these expressions involving radicals, is to multiply top and bottom by the conjugate. That is, this expression with the opposite sign, so that would be a plus sign in the middle. Instead of root x plus 1 minus 3, it would be root x plus 1 plus 3, and numerator and denominator. Okay, let me write limit x goes to 8. Okay, let's multiply the numerator. We're going to FOIL this out. First times first is x plus 1. Because we're multiplying conjugates, the outer plus inner are have opposite signs, and they drop out. Last times last is minus 9. And in the denominator, recall that we want to cancel the x minus 8, so don't multiply through. Keep it in the form, in the factored form, x minus 8 times that square root x plus 1 plus 3. So notice in the numerator, x plus 1 minus 9, that is equal to x minus 8. So we have, just rewrite once again, we have x minus 8 in the numerator. And it's going to cancel with this x minus 8 in the denominator. And after we do this canceling, now we can take the limit. Just substitute in x equal 8 at this point, and we have 1 over square root 8 plus 1, 1 over square root 9 plus 3. That's 1 over, this is 1 over 3 plus 3, so that's limit 1/6. Okay, number 8, we want to, well actually, in the next group, we want to determine if the given function is continuous at the given point x equals c. In our first example, we have f of x equal to 5 over x minus 2, and our value is x equal 2. So this f of 2 does not exist. So the first part of the definition of continuity is violated. Let me just remind you of the definition of continuity. I think we have it a little bit further down. Let me just take a look one second. So here we have the definition of continuity. There are 3 conditions. A function is continuous at x equals c if, first of all, f of c exists, that is, c is in the domain. The limit as x goes to c exists. And b and c are equal. The limit has to be equal to f of c. All right. Okay, let's go back to problem 8. First of all, f of 2 does not exist, so right away we know discontinuous. But we have a few choices here. We have discontinuous and non-removable, and discontinuous and removable. Okay, so in removable requires that b is true, that the limit as x goes to c of f of x exists. In this case, f of 2 does not exist, so that would be a. And so a is not true. Okay, so in order for a function to be a discontinuity to be removable, so 2 is a discontinuity because a is not true. So in order for it to be removable, b must be true. But what do we have in case b? Does the limit as x goes to 2 of 5 over x minus 2 exist? No, it doesn't, because the denominator is going to 0. So this limit does not exist. All right, so b is not true as well. Now, since b is not true, that means non-removable. So it's discontinuous and non-removable. So we're going to choose option C. Okay, let's look at number 9. We want the limit as x goes to 2. Well, this is the limit as x goes. Well, let's first do a f of 2. 2 is in the domain. 2 doesn't make the denominator 0. It makes the numerator 0, but not the denominator. F of 2 is actually equal to, if you substitute in, we get 0 over 7, which is 0. So a is good. B is also good. The limit as x goes to 2, just substitute in 2 and we get 0 over 7. The limit exists, and the 2 are equal. So C is true as well. So we have continuous at x equal 2. Okay, let's look at number 10. All right. First of all, A is not true. F of 2 does not exist. F of 2 does not exist because of this x minus 2 in the denominator. So the function is discontinuous. But how about B? B actually is going to be true. The limit as x goes to 2, I'm going to factor this right away, x plus 2 over x minus 2 divided by x minus 2. Once we do canceling, is equal to 4. So the limit does exist. So B is true, which means removable. We still have discontinuous because A is not true, but the discontinuity is removable. So B in this case. Okay, let's look at number 11. We're talking about limit as x goes to 2. Okay, so let's just simply, plug in 2 top and bottom, and we know that if it's equal, then the limit will exist. If not, not. So let's do that quickly. Plug in 2 here, and we get 7. Plug in 2 here. 3 times 2, we have 6 plus 4, we have 10. So we see that the limit doesn't exist. So B is not true. A is true. F of 2 is equal to 2 plus 5 is 7. Just plug in right here. But B is what fails. That's what we were just looking at. The limit as x goes to 2 from the left is equal to 7. The limit as x goes to 2 from the right, substitute in 2 here, and we have 10. These are not equal. Okay, so the limit does not exist. So B is not true. That means discontinuous, and since B is not true, non-removable.